Everybody ready? No. Yeah. Okay.
Okay.
Our next speaker, Anton will introduce our next speaker. And Anton, please.
So, hello everyone again. Today I'm glad to introduce our new speaker, Dr. Alex Weber-Tate. Alex is a senior developer engineer working at the CPI TMD within the applied science team. He was awarded his PhD in 2022 from the University of Liverpool for the design and commissioning and building of an upgraded rubidium atom interferometer. He played a key role in the implementation of the optical system required for cooling atoms and the manipulation of their energy states. He went on to work as a research associate at the Cockcroft Institute in Daresbury laboratory, using his experience in optical and laser systems to contribute to the high luminosity upgrade of the LHC. He started working at TMD in January 2022 as an atomic physicist, working on quantum navigation using atomic interferometry. And right now, Alex will tell you about his work there. So, Alex, I'm happy to give you the floor.
Thank you. Thanks for the introduction. I'm going to try today to just give you an overview of what kind of quantum technologies are used in industry, what the opportunities are, maybe outside of an academic context, and the kind of real world applications of some of the stuff you've been learning over the course of this school. So, just to give a caveat, I'm coming at this to try and give a general overview. It might not be as technical as some of the other talks you've been listening to, but I am a scientist first and foremost. I don't have a corporate background, I have a science background, so it'll probably leak in there. So, just to kind of give you an overview of how the talk's going to go, I'm going to kind of give you an indication of what the company I work for does, kind of who they are, what their history is, some of the motivations for quantum PNT, so position navigation and timing, why it's important, why it's needed, and why there's a lot of interest in it now. And then the bulk of the talk is going to be about the projects we're working on, and try and give you a sense of the kind of things that we do in the quantum space. And then just go over kind of the state of the quantum industry, what opportunities there are, what kind of things are being looked at, and try and give you a kind of clear idea of how much of an exciting field this is to get into. So, TMD is not traditionally a quantum company. They basically make high power microwave and RF equipment. And its primary niche is that it's used in quite extreme environments. So, these are the kind of classic things that they've been making for years. And over the past 5 or 6 years, we've moved into more quantum products, so clocks and sensors, with the kind of application towards PNT. So the kind of history of it, so it was formed in the 40s, part of the MI, Microwave Tube Research Division, and became Varian, went through a bunch of iterations to where we are now. So we've been there since the very beginning of radar, and going up to even the most modern systems. So now to some of the interesting points. So the motivation for why people are so interested now in this quantum PNT is the reliance that we have on GPS. So GPS is, it would be an understatement to say, completely revolutionized kind of how we navigate and how in industry and in defense and in shipping and all of this kind of thing, how important that's been. So, what a lot of people don't always realize, though, is that it's not just a standard for navigating, but it's also a standard for timing. So, a lot of devices get their clock signals from the atomic clocks that are on the GPS satellites. And there's a really heavy reliance on that across the world. So, used for comm synchronization, time stamping, all of these kinds of things. The problem with that is on Earth, GNSS satellite signals are very weak. They can be easily jammed, easily blocked, and easily spoofed. And there's no real way of preventing this. There's a lot of creative solutions, but the inherent technology has these problems. And I'm sure I don't need to tell you, there's an increasing kind of GNSS jamming and spoofing activity from all over. So there's a kind of map on the right there. I think it's from a few years ago, so it might not be most up to date of just how that kind of spoofing activity happens. So there's a lot of interest in having these local atomic clocks, local oscillators that allow for holdover in GNSS denied environments. And the kind of long and short of it is a better clock will give you holdover for a longer period. So while you might not need the best clock in the world if you're only down for a few minutes or an hour, if it's over longer periods, you need to have these really good clocks to provide this holdover. So the way that the company got into these kinds of quantum technologies came from a project that we did with the University of Strathclyde on making a grating magneto-optical trap. So it's a optical trap where the balancing beams that cause your cooling, your atomic cooling and trapping, they are produced by a grating rather than by your traditional 6-beam magneto-optical trap. And what this does is it allows you to really shrink down the form factor and make these traps quite small because they're done with a single input beam on a grating. And the trap that we've created, again with lots of help from Strathclyde, it was their technology originally. We can trap around 5 million rubidium atoms on this grating, and they are pretty stable in there. You can move them around. You can put them into more compact systems quite stably without having to worry too much about things like vibration isolation and all that kind of thing. And I'm sure I saw you had a talk on atom interferometry before, but these trapped atoms can be very sensitive to external forces, and therefore they can be used as a very sensitive sensor. These sensors can be used to do things like navigation, can be used to do things like magnetometry, and they can even be turned into clocks. And a kind of side thing is because of the simplicity of the technology, they can be used as teaching aids. So you send one of these things to a lab, all they need is a laser, they plug it in, and that works. So this was turned into a kind of product. There was a paper released by it for it, and we then kind of moved on to how can we spin out this into a useful sensor for doing metrology. So just to go into like what the kind of thing looks like, this is a picture of our atom trap, produces a few million atoms, and we want to use this as a starting point for sensor applications. We're actually currently on the pump. Sorry, the actual small metal thing on the back of the GMOT, that's actually a small ion pump, but we're moving towards having the whole thing passively pumped, so it could be made even smaller. That's a kind of development coming later. So what kind of technologies can we spin this out into? Like I said, we have a standalone product. We have a prototype for a gravity gradiometer, which is essentially two of these connected in the same vacuum chamber by a bit of pipe, and then you can do simultaneous trapping in both of the things and interrogate them with the same laser beam, get some gradiometry. More recently, we've been working on the Harlequin project, which is an inertial navigation system using a GMOT as a quantum accelerometer. So that's been a big project we've been working on, and probably I'll talk about that in a few minutes. So this gradiometer is a portable gradiometer, and it's based on two connected GMOT units. The actual dimensions of the thing is about around 40 centimeters. So it's really quite a small device, obviously not including the lasers, but it's a way you can kind of do some of these larger scale experiments. So you don't quite need the precision of say the really long baseline ones. These sensors can give you still increased performance compared to some of the classical ones, and they have other inherent advantages over these. So this was a project again in the collaboration with University of Strathclyde and M Squared, who are providing the laser. And yeah, it just kind of shows the where we can push these kinds of projects to. And there's some kind of more detailed diagrams of the chamber itself and some of the collaborators we were working with. So the Harlequin project was a project to try to develop a one-axis quantum hybrid inertial navigation demonstrator. So it was an 18-month project involving lots of other subcontractors. So these kinds of work, when you are doing this in an industry context, usually you have big collaborations with lots of other companies too. The amount of people working on things like this, even if it's not on the system integration, if it's working on the lasers or the kind of mechanics side of it, these can be big projects. So it's a sensor based on the technology I was talking about before. And the idea behind it was to not make a dedicated quantum navigation sensor. It was to do a hybrid system where your quantum system disciplines your classical system. So classical accelerometers are actually very, very good. The MEMS ones are very accurate and they're very fast, but they suffer from a bias drift, and it's almost impossible to eliminate. You can make better and better devices, but they all have this bias drift, and you can lose lots and lots of distance, kind of accuracy distance, within hours. So the idea is to have this quantum sensor that is drift free to condition your classical sensor. They work together. You perform some sensor fusion on the system, and from that you get the accuracy of an atomic sensor with the rep rate and kind of robustness of a classical sensor. So global navigation satellite systems, yeah, like I talked about, revolutionized navigation and timing, but they don't work underground or underwater. The signal is weak on Earth, and spoofing can cause multiple issues. And there's a lack of reliable redundancies out there. The basic idea behind inertial navigation is essentially based on dead reckoning. So it's been around for a few hundred years. Interestingly, as the initial developments behind good pocket watches, mechanical clocks, back in when navigating was very, very important. But the idea behind it is if you know where you start and you know exactly your accelerations in your kind of three cardinal directions, as well as your rotations, and you have a very good clock, you work out where exactly you end up just based on these inputs. So the inertial navigation systems, all of them are based on this principle of essentially dead reckoning. Like I was talking about before, the drift causes uncertainty of tens of meters after an hour of operation, and you get this accumulation of systematic errors because each measurement is referenced to itself. And the current commercial INSs, so the inertial navigation systems, they also use a holdover, but they use GNSS to do that, which obviously, if you want them to be in place when GNSS doesn't work, there's a problem there. So a higher sensitivity device relying on fundamental physical constants will provide a much better high accuracy reference. So in terms of options, when it comes to navigation, you've got quite a few. So one is magnetic map matching, where you get a really detailed picture of what the ocean floor looks like, or wherever you're going over looks like magnetically. And with a really good magnetic sensor, you can use that to know exactly where you are. Celestial navigation has, of course, been around since humans have first started to travel, and inertial navigation is the one that we're interested in, the one that I was talking about. I am aware you've already had a talk on atom interferometry, so I'll just fly through this. It requires a simultaneous interaction between two electric fields. You excite an atom into an intermediary state, and depending on your detuning, you can end up exciting into a higher order ground state through an intermediary excited state. So the general process is you cool atoms down in a magneto-optical trap and then do some post-Doppler cooling to get them even colder. You put them in a specific state, you split them up, allow them to propagate, invert the state populations, combine them, and then measure those state populations. And by measuring those state populations, you can generate interference fringes that give you your information. Again, fly through this. They're sensitive to these. They're sensitive to this, and you end up getting by that last term there, you can get an acceleration out depending on how long you allow them to freely propagate. So the system that we use is a Mach-Zehnder style interferometer. The pi/2 pulses act as like beam splitters and mirrors, and this is the kind of general scheme of the interferometer we're using. And here's just a picture of the GMOT and surrounding shim coils. It has an integrated patch antenna to provide microwaves, also used in state selection. External shim coils for magnetic field cancellation and generating a quantization axis, and it will be surrounded by a two-layer mu metal passive shield, which are actually very good at meaning you don't have to constantly recalibrate your magnetic field cancellation when you're kind of moving around. So the other project that I worked less on, so if you have any questions about it, please be kind. It's a rack-mounted atomic clock. It uses a calcium ion frequency standard. And this technical approach was chosen because it has a very high precision and can be made reasonably small and using mostly off-the-shelf components. So this is the general way that the SIF's atomic clock is used. It's a single ion, uses 6 lasers to cool, trap, and interrogate it. And a lot of the wavelengths that you can use to interrogate this calcium ion are standard telecoms lasers. And there are a few that we've had to develop with the University of Sussex and a bunch of other partners over the course of the project. This is the kind of things that go into this system. You've got the electronics, the laser cavity, spectroscopy chamber. We focused mainly on the spectroscopy chamber. One of the things that the company is very good at is making compact and ruggedized vacuum chambers and vacuum systems. So we were very involved in the creation of that spectroscopy chamber. And this is the kind of place on the buffet of timekeeping that we expect to sit at in terms of its performance compared to the very best clocks that you use in laboratory experiments to the kind of standard 5071A that's been around for years. And we think that there's a niche that this clock can provide when compared to some of the other competitors. Something that we've gotten into quite recently, again with the University of Strathclyde, is the idea of using this rubidium trap as its own microwave cavity clock. So the idea is, instead of trapping the atoms in some arbitrary geometry of like a cube, you actually make the housing for the atom trap a microwave cavity. And using that, you can get a lot of advantages in long-term stability. And there's also a lot of potential for making this quite ruggedized. It's not aiming to be the best clock in the world, but what it is aiming to be is a few orders of magnitude improvement over the compact atomic clocks that currently exist. And there's potential for ruggedization that means that it can be used in less ideal environments, let's say. So we've got some future work. We have a 24-month project to test and develop Harlequin, that's the navigation system on a ship. We have a trial facilitated by the General Lighthouse Authority in the UK, so that's been organized. We have a ship to put it on, and we're eager to see how well it's going to perform. We fully expect this to guide the upgrade path. So the problem with doing a lot of these systems is you're not quite sure how much better they're going to be until you actually test them. So depending on how well that goes, then we'll know what we can improve, the kind of direction of the project, and where we go from there. So we have 2 trials planned. The first trial will be sometime in June, and then another one later where we can implement the upgrades, and hopefully have another one which will be the real tester of how well the system performs. So the applications of quantum are pretty widespread and pretty profound, and a lot of people are getting more and more into it. So quantum computing, I'm sure, is one of the big ones that a lot of people know a lot about. Also, communication encryption. There's imaging, quantum imaging techniques, and also magnetometry techniques. So there's an interesting space for that. There's navigation, geology even. There's a few companies that are using essentially gravity gradiometers to measure volcanic activity on volcanoes and things like that, and gravitational sensing as well. One thing I didn't mention in the navigation options is there's another thing called gravitational map matching, where you map out the individual really small differences in Earth's gravity as you travel. And if you can track those, then you can know where you are as well. So in terms of the companies, there are hundreds of companies developing quantum technologies. They're used in lab systems, telecoms, defense, shipping, healthcare, logistic and supply chains. There's a real appetite for really developing this in industry. And I think that that this is now a very good time to start getting into quantum sensing, especially because it's not just startups anymore. It's kind of big companies is realizing that this is something worth investing in. And in the US, the UK, and across the EU, there's lots of investment opportunities for these big kind of quantum companies to develop. So it's a really exciting time to be getting into this kind of industry. So that's all I've had. I think that will give you enough time to ask questions and have lunch on time. So thank you for the organizers for inviting me to this. It's been a pleasure to speak to you all. I'm happy to take any questions you might have.
Thank you very much. Thank you very much for your answers. So, some questions or comments from the audience? Anton?
Currently, there are no questions from online, so maybe there are some questions from the audience.
Here I do not see at the moment. Yeah. Nobody has.
We still have we can take 5 minutes for people to think or something.
Yeah. Because it's really funny. But I have such a practical question when it's possible to make. We are in Ukraine discussing a lot of application this technology. I mean, accelerometry and gravimetry for small flying apparatus, drones. Yeah. So far, I see it's not realistic because they're quite large, quite massive. How do you estimate? Is it possible that in nearest future these devices will be miniaturized such that one can use them for such a more smaller applications, smaller?
Yeah, so that's kind of the thing that we're really trying to do soon. So the weight requirements of something for acceleration sensing or gravity gradiometry, the actual sensors themselves can be made pretty small. So the systems we have weigh maybe like 5 kilograms, which I know for like a lot of the smaller drones is a bit prohibitive, but larger ones is a bit better. The problem with all of this is your laser requirements. The lasers are still very heavy. And in order to provide like a good enough laser signal with all the electronics and heat sinking and stuff like that, that's where the problem comes in. So I think that the laser requirements are the things that will need to improve. But I would say maybe within 5 years, it's possible to have quantum sensors in that kind of form factor. We're aiming for things that are a bit easier to start with. So that's why we have shipping sea trials, because we think that that's kind of a good place to start. But the eventual goal is definitely to have these kind of sensors portable enough to put on something like a drone. There's another approach, which is using integrated optics. So basically optics on a chip that a lot of places are experimenting with now. That's not my field of expertise, so I'm not sure how well that's going to develop and how quickly that's going to develop. But if that became well understood enough and tested enough, then that could speed up the timeline immensely.
Okay, thank you very much. It's very nice to hear that this is only the question of lasers. So this may be a big question. But another question is, for example, whether it's possible to, we see one more question from online. Okay, Anton.
Yes. So there's a question from an online audience. You mentioned atom trapping. I'm curious to know how atoms actually trap in the center. If it's slightly at the different position, then what will happen with magnetic foil?
So it's done so that the trap doesn't form in the middle of the chamber. It forms about 6 or 7 millimeters away from the grating. and where it forms depends on the grating spacing and the angles as well. So you can have some customization of that, but you essentially form quite a large trapping region in terms of your balanced laser beams. And you can essentially shift the trap's location by shifting your magnetic minimum of your quadrupole field. In terms of how finely tuned it is, you usually have a few millimeters where you can play with in the trapping region. But it's been really, the way it's been engineered, it was engineered by a company, a spin out of Strathclyde in Glasgow, was basically to create this grating as such so that it can have this balanced trapping region where the incoming beam is balanced by the beams coming in this way. So when you kind of work out the angles of them, you do have this balanced trapping region. It's analogous to a pyramidal mott, if you've ever come across those actually, but using a grating instead of the mirrors.
Thank you. Anton, one more question?
I actually have a question, but I'll first of all, Andrei, you can ask your question, and I'll
Yeah.
ask
Okay.
mine.
Somebody here has? Yeah, we have one question from students, and after that, mine maybe.
Okay, thank you for your lecture. I have a question, maybe I don't understand, but what can be a range of area that one sensor can work with?
What range of error can it work with? So
yeah, what area we can measure, in what area we can work with one sensor of gravity gradient or something.
So it's there's
sorry. Yeah.
Sorry, what was that?
I mean, what's this?
Domain of values for parameters, yeah?
How big can be area in space that we can describe using one sensor?
Right. So in terms of what it could, so the acceleration sensors are sensitive just to how quickly you're moving, but there is a bandwidth to that. So the reason why we're doing a quantum and classical hybrid system is that there's a fundamental limitation to where you end up. I've got a slide somewhere. So when you sweep out a fringe, you essentially have this. You have an interference pattern, but the quantum sensor will only tell you where on this fringe you are. So one measurement for one shot will tell you where on this fringe you are. We use a classical sensor to tell us which fringe we're in. So the classical sensor tells you what fringe you're in, and the quantum sensor tells you where you are on that fringe for the additional precision and accuracy of it. The other thing that you can get limited by is if you're accelerating too quickly, which is what kind of hampers this on like aerial vehicles, is that your atoms will simply fly into the wall of your chamber and you won't have time to measure them. So there is like a fundamental limitation to some of these quantum sensors, especially ones based on cold atom traps. But we're trying to get around it by having a hybridized system that compensates for this kind of stuff. I hope that's answered your question. I wasn't quite sure if that was what you meant.
Yeah, okay, thank you.
Yeah. Okay, thank you. I have such a question. During this school, we have learned something about another kind of navigation system and also quantum navigation system based on Sagnac effect. Yes, so not only optical, but also atomic and even in graphene solids Sagnac effect. And we know that this is also based on phase estimation. Phase estimation can be improved for example, for non-classical light. It's also well-known results. Could you please compare these methods with methods based on Sagnac effects?
Yeah, there's lots of different approaches to this kind of problem, right? One of those is the Sagnac effect. The Sagnac effect is more for is very important for quantum gyroscopes, right? So the problem with the one of the main problems with using this kind of navigation method is one of the main sources of uncertainty you have in these things is your rotations, and this current sensor doesn't address that. In terms of where we would go in from to make a 6-axis system, I think a sensor based on the Sagnac effect would just be used in conjunction with something like this to kind of provide your rotational measurements. In terms of how it compares just for pure acceleration, I'm not quite sure. I don't quite know. The problem with this system is we don't know how good it's going to be until we try it, and we haven't got enough data to see how good it is yet.
Okay, thank you. Anton?
So yeah, basically I have a more like industry, like a little bit tricky question about comparison between general state of like industry in quantum computing and quantum sensing. Because what we've seen recently, for instance, from quantum computing development, that there was like a lot of investments going into there, but not many outputs because like realistically speaking, we're very, very, very far away from development of like a real practical quantum computer. And so like a lot of people talking about like this bubble of quantum computing we're trying to explode. So I'm curious, where is the quantum sensing in this stage? And like, is there any possibility that it will follow the route of quantum computing, or the palpable outputs will be much more sooner? So yeah.
Yeah, that's a very good question, actually. I like that. So, yeah, quantum computing has had a lot more investment in it than quantum sensing has. I think that's because quantum computing has these promises that are immediately tangible to people who want to invest a lot of money, and it has possible applications for everyone. The applications for quantum sensors are still a little bit niche, so there's been a lot less investment of it, and yeah, the amount of money that's certainly put in forward for research on quantum sensing is small compared to the venture capital that you get for saying you're going to build a working quantum computer, right? And I think with quantum computing, there's this sense that no one wants to be caught out if someone does make it work. So everyone has to invest just in case you're left behind. That hasn't quite been seen in quantum sensing yet, although I think it is ramping up. I don't think it'll ever hit the same levels as quantum computing, just because I think the use cases, there's less potential for mass scalability, and there's less potential for making multiple billions of dollars from it. But in terms of where we are in compared to a usable sensor, I think we're reasonably close. So I often think, interesting in comparing it to, say, classical computing. I know I'm kind of crossing comparisons now. I think where we are in quantum sensing is where we are in computing during like the 40s. So all of these sensors are very big, they work, and we can get them to do specific functions, and they're practical in really kind of specific environments. And then the kind of shrinking down and commercialization stage will happen in 5-10 years. So in terms of like a usable output, we're pretty close. I mean, the navigation system that we've been working on, although not a kind of 6-axis fully working system, I could see something by someone, maybe not us, maybe there's a company in France called Exail that have done a lot of work on this, and I think they already have pretty much working quantum sensors. It's just getting more data out of them, testing them, and refining them. So I think in terms of a kind of definite output, it's a lot closer than a working quantum computer is.
Okay, great. Thank you very much.
Anton, do we have more questions?
No more questions from online. So yeah.
From local audience? We also don't have. Let's thank our speaker again. Thank you very much. Thank you very much for being here. Yeah.